say in all the models that we considered so far, starting from the governing equations, we have been focusing on laminar flow. Or in other words, there was nothing which could have helped us include the effects of turbulence in that. So turbulence certainly has a strong impact on many of the exchange processes related to the flow. So that has to be incorporated whenever it becomes when relevant from the flow conditions. Uh, at the same time, there is no uh, analytical approach which can help us have closed form equations or solutions for turbulent flow. So the solutions for turbulence are either qualitative relations or quantitative data, which are just in terms of experimental correlations. So when I say qualitative information is just as functions, that is just functional relations. We will probably won't even know what exactly is going to be that function, but we just know that these are the parameters that are going to influence turbulence. And we also have some experimental correlations, which are purely based on empirical findings, and they also help do calculations in turbulent flows. We won't be attempting to do any calculations in turbulent flow, but we'll just look at what marks the onset of turbulence and what are some of the physical, the important influence of turbulence in the flow. Many of the observations that we make here applies to any kind of flow. That is comparison between laminar and turbulent. The main influences will be probably comparable across all regimes of flow. That is subsonic, supersonic, hypersonic, etc. So many of them may be common, but we'll also look specifically what matters significantly as with the particular emphasis on hypersonic turbulent flow. The transition. Probably would have come across this in fluid mechanics, not necessarily, but the transition from laminar to turbulent flow happens because of several factors. Could be partly because of the free stream turbulence, could be because of roughness of the wall, uh, instabilities in the flow, other geometric parameters, etc. But in any case, when you consider a simple configuration like this, like a flat plate, usually a region can be identified in which the transitional effects are more. That is, between the purely laminar region and purely turbulent region, you can identify physically a region which is sort of unstable in its character, unsteady in its character, and which has a little bit of laminar properties as well as turbulent. So that kind of an area, region is referred to as the transitional region. So that's where you expect the turbulent effects to be starting to be prominent in the flow field. And once the flow becomes turbulent, many of the basic characteristics will change. We'll know for sure, for example, from the uh, uh, pipe flow analysis, you know that the boundary layer, the rate of growth of the boundary layer is different. That is, in a laminar flow, you will have a parabolic profile, whereas in turbulent flow, you have a flatter profile, which is referred to as top hat profile, etc. What matters here is the difference, or the rate of growth of the boundary layer. The laminar boundary layer takes more this one to grow, whereas a turbulent boundary layer grows faster, and that's the reason why it is thinner in the case of internal flows. Okay, so there are several factors that leads to the turbulence. Sometimes when it is essential to incorporate those parameters, obviously the skin friction, heat transfer, etc., are important even in the transitional region. So, but at the same time, there is no theoretical means to exactly tell when the flow starts becoming turbulent. Of course, we say based on Reynolds numbers. So we say that if Reynolds number is such and such regime, it is turbulent. But then the question is, when will that turbulence set in, or what causes the turbulence to set in? And there are no theoretical means to exactly say when the transition is going to be, but there are parameters which are found to be influencing the turbulent transition. So based on that, for each configuration, a transitional turbulence number is defined as rho v x divided by mu rho v xt divided by xt. In the case of flat plate as shown here, the transition is just to be considered to be as a function of the length. So all other parameters being insignificant, like the free stream turbulence and other things being insignificant, what we can say in the case of flat plate configurations is that the transition can be a function of the axial distance, the streamwise distance along the flow. So that's the reason why it is function related to RET, that is the transitional number is transitional Reynolds number is related as a function of xt. What happens during transition and after transition? This sketch I have taken from a fluid mechanics book, so it applies. What I want to say is that this applies to all, across all regimes, as I mentioned earlier. The qualitative aspect of the qualitative aspect of the differences pretty much remains similar. So in the laminar boundary layer, you have, as we know, the laminae of fluids. So it's relatively more orderly, whereas when turbulence sets in, the chaotic behavior also sets in. And then gradually, and more importantly, that is, it's unsteady also. The region of transitional turbulence is somewhat unsteady. Unsteady means it can have fluctuating components. Which makes it even more difficult to predict the onset of it. And that's one issue that people have in predicting the onset of turbulence, because it's the onset itself is unsteady in its nature. Whereas when it becomes fully turbulent, then the exchange processes becomes more prominent, and the boundary layer will change, will have a distinctly different characteristic as opposed to the laminar boundary layer. And there will be, in accordance to that, there will be other parameters, the various strengths and shear stress, etc., within the boundary layer. So these three regions, laminar, transitional, and turbulent regions, they can occur in any flow, subsonic, supersonic, any hypersonic, etc. So at this point, I want to warn you about possible confusion between the terminology, Reynolds number and Mach number. So I just want you to be aware that these two are independently quantifying certain parameters which are important for the flow. Independently, they are two different groupings. They are independent. The only common factor in these two is velocity, right? Rho vd by mu, v by a. So velocity is probably the only connecting parameter for the two. Except for that, that non-dimensional grouping per se reflects different aspects of the flow, which means that it is possible to have, as we know, a turbulent subsonic flow. It is possible to have a turbulent supersonic flow. It's possible to have a laminar subsonic flow. It's also possible to have a laminar supersonic flow. Okay, and similarly, you can have turbulent hypersonic flow. You can have laminar hypersonic flow as well. When I say laminar, I just care about Reynolds number. When I say hypersonic, I just care about Mach number. I don't check the Reynolds number, right? So when we categorize flows as subsonic, supersonic, hypersonic, etc., we never bothered about Reynolds number. It's independent. So similarly, when we say laminar and turbulent, we don't care about Mach number. We just talk about the ratio of inertial forces to viscous forces, which is Reynolds number, right? So it's possible to have hypersonic flow, which is laminar in character, hypersonic flow, which is turbulent in character, and similarly, subsonic flow, which is turbulent in character, and vice versa, subsonic laminar flow. And same way in supersonic also, you can have turbulent and laminar flows. This I'm just just saying this so that when you think of the two parameters, Reynolds number and Mach number, you should be treating them separately. The only connecting point is viscosity, but velocity. But what matters is the non-dimensional grouping, which is independent. Okay. Now we focus on the most important transport processes, means exchange of momentum, exchange of primarily the exchange of is heat transfer. These are the two things which are strongly influenced by two. And when in a laminar boundary layer, we know that there is velocity gradient, there is a shear stress, there is transfer of energy, there is a dissipation of energy, etc. But all that happens at a microscopic scale. That is, we know that the exchange, the shear exchange between layers is because of intermolecular action, right? That is the cohesion between the molecules, right? So it's a microscopic scale. It's at microscopic scale. The same way, heat transfer also is dominant by the molecule to molecule interaction, right? So that is when the flow is laminar. And that is where we use the dynamic viscosity, etc., to calculate the shear stress. Whereas in turbulent flow, layer, there is mixing across the layers. So I guess it should be easy for you to visualize, because laminar, the word itself means that it's like laminate. That is, you have layers of the fluid, one over the other. So the layer to layer exchange is what matters there. Layer to layer exchange happens because of the molecular transport, intermolecular transport. So that is laminar. Whereas when you say turbulent, the layers are broken. The fluid is actually mixing at a larger scale, a macroscopic scale. That is, you can actually visualize the small eddies or small vorticity which are existing and manifesting and growing and breaking, etc., within the turbulent region. So mixing is at a macroscopic level, not at the molecular level. Is turbulent, and that is characterized by the small eddies, movement of small eddies across. The rate of energy transfer, the rate of momentum transfer, and the rate of energy transfer are all higher in the case of turbulent flow, in turbulent boundary layer. So in a laminar boundary layer, you have all these, but the rate high, you have turbulent flow, and that is because of the increased mixing, or the actually the mixing becoming, and that's where we see the difference between the two boundary layers. So what we observe here readily is that when you have a laminar boundary layer, please say in this you have along the x-axis you have the streamwise velocity component u, and the transverse axis is y. And we see that both the two different this ones, but they reach the same free stream velocity. Let's say u infinity or v infinity, whatever it is. So, but then if the flow is turbulent, the achieving of this free stream velocity is happening much earlier, right? Much earlier. They say somewhere here, very close to the value of u. Whereas in the case of laminar flow, it reaches. I mean, it should go to a higher value of u to reach that value. I'm sorry. Say here the y coordinate. This one would have almost close to the free stream velocity when the flow is turbulent. Whereas in the case of laminar flow, it's much later. So the rate of growth is the rate of growth, the rate of exchange between the layers is much more prominent, much faster in the case of turbulent flow, and that is what is reflected in the velocity profiles for the two cases. So if we have a top hat profile for turbulent flow, it is because the exchange rate is much higher because of the molecular, the macroscopic interaction. And then what we are talking about is transition. When do we say the flow transitions to turbulent flow? We just said that we can characterize the Reynolds number as RET is equal to rho E UEXT divided by mu E. But then what are the parameters which will determine that RET? That is, how can I say whether, yes, at this Reynolds number, the transition is going to happen? Actually, we don't have any conclusive theory so far on that, but people have found out that there are large number of variables. I've just listed the, I mean, it includes the Mach number, the inclination, the temperature, mass flow rate at the wall, angle of attack, Reynolds number per unit length, etc., etc. A lot of things. We don't go into each of them, but what I'm saying is that there is a large number of parameters which influence the transition to turbulence. So it is, I mean, this importance of this number is that it is so unclear that we unclear to say when we can define the flow to be undergoing transition to turbulence. So all those transitional numbers, etc., that we see are purely empirical in nature. We don't have a theoretical way to predict them based on the parameters that are of interest. Okay, so now coming to, so this all what I mentioned so far is applicable across all Reynolds numbers, all Mach numbers, or across all regimes of flow in terms of subsonic, supersonic, hypersonic, etc. Now, specific to hypersonic Mach numbers, it is observed that the transition to turbulence is delayed at higher Mach numbers. That is, when the Mach number is high, the flow tends to remain laminar for a longer period. Okay, so this is where again the distinction between Mach number and Reynolds number should be recalled. There are two different dopings, as I mentioned. Now the question is, if I have a flow, a hypersonic flow which is laminar, when can I expect, at what value of Reynolds number this can be expected to transition to laminar turbulent flow? And experimental findings show that, again, purely experimental. We don't have a theoretical model probably to arrive at that value. Not probably, certainly we don't have a theoretical model for that. But then experimental findings show that the transition to turbulence is delayed in hypersonic flows. That is, lower Mach numbers. That it's usually, I mean, low speed flows. Usually 5 × 10⁵ is considered to be a transitional regime for external flows. External flows, okay, not the internal flows. Internal flows is where we say 2000, 2500, etc. for pipe flows. But when we talk about external flows, 5 × 10⁵ is usually where the which is given as the transitional range. Whereas it becomes much higher, magnitudes, orders of magnitude higher, that is 1 × 10⁸, etc. in hypersonic flow, which means that in hypersonic flow, the transfer, momentum transfer, energy transfer, etc., heat transfer, etc., are still dominated by laminar effects, even up to this range, 1 × 10⁸. Only beyond that, it becomes high. Becomes in the turbulence range. And this in essence is beneficial because the effect of turbulence is to increase the rate of it, etc. So for example, the wall heating during re-entry, etc., will be higher when the flow is turbulent. So if it is restricted to laminar, this one, the rate of heating, the rate of thermal energy transfer, etc., will be low. Angle of attack, not going to through this ones, but then the observation is that with increase in angle of attack, the flow, the three-dimensionality increases. Because of that, the transition to turbulence also increase. It becomes faster or more prominent. That is. Now, once the flow transitions to turbulence, when we try to model it in the sense numerically, you don't have flows from analytical relations for that. But even when you model it numerically, you need to have some parameters which can quantify the extent, the magnitude of turbulence. And one parameter which is conveniently used for this in this context is eddy viscosity. Concept of eddy viscosity, I probably would have heard of that in CFD. The concept of eddy viscosity comes by drawing analogy to the dynamic viscosity mu in laminar flow. It is as simple as that. In laminar flow, we consider mu to be responsible for the momentum transfer, the shear stress, whereas in turbulent flow, the corresponding value mu due to eddies. So in this way, when you have turbulence, the dou u by dou is otherwise multiplied only by mu laminar flow. So this mu t into dou u by dou y is added to the dynamic viscosity mu. So that parameter mu t is referred to as the eddy viscosity or the turbulent viscosity. Sometimes it's called as turbulent viscosity. In CFD usually is referred to as eddy viscosity. And this is transfer. Accordingly, in heat transfer, the parameter, the similar parameter is used actually that it's slightly roundabout way where you use the Prandtl number. We know that in laminar flow, we have seen that Prandtl number is defined as, which I have said this mentioned about it many times. Prandtl number is a fluid property mu Cp by K, whereas mu, Cp, and K are the dynamic viscosity, specific heat and conductivity of the fluid, of the gas in this case. So mu Cp by K is used as the turbulent flows. A similar parameter is defined as turbulent Prandtl number, in which Cp is retained as the same value and mu is replaced by mu t and K is replaced by Kt. Reason for this is Cp, the specific heat constant pressure, that does not change with whether the flow is turbulent or laminar. At the same time, as we have seen, mu will be the effect of shear stress will be higher, or rather what causes it will be more. It is not limited by the value, molecular value of mu. So that is separately denoted as a d viscosity or turbulence. In heat transfer, the molecular heat exchange will become more prominent. So that will be that instead of K, the turbulent conductivity Kt is used to define the turbulent Prandtl number. So turbulent Prandtl number is defined as mu t Cp by Kt. That is, as we have K in laminar flow, mu Cp by Pr. In turbulent flow, Kt is calculated as mu t Cp by Prt. The reason for this kind of a formulation, which may be sort of confusing first, because I'm relating Kt to mu Tcp by Prt, whereas Prt is usually not known. So how do you calculate Kt? The answer to that is the reason for this representation is that in many cases this ratio Pr can be assumed to be unity in the case of turbulent flows. So in turbulent flow, the Prandtl number is often as a practice and also supported by some observations that it's safe to consider it as close to unity. So PRT is taken as unity, which means that if you know the turbulent viscosity, you can calculate the parameter called thermal conductivity, turbulent conductivity, as mu T Cp PRT. And the value of that, the magnitude of that is going to be certainly higher than that for the K. The Sorry, so the interruption in between. Okay, the value of turbulent thermal conductivity will be significantly higher than the value for the molecular property, or rather the fluid property conductivity, which is used in laminar. Now, coming to the most important parameters or the fan and heat transfer. Why they are here important? Because wall friction is what basically gives rise to the skin friction drag, that is the shear forces at the wall. And so the aerodynamic forces are strongly dependent on the wall friction, and heat transfer for obvious reasons, since the flow is integration near the wall is going to have dissipation of thermal energy and excessive heating at the wall. So wall heat transfer, both these are important. And what is the impact of turbulence on that transport that we just discussed about? That is the eddy, the movement of the eddies, and the transport of energy and momentum caused by the movement of eddies. These create the higher rates of energy transfer. So the thermal energy transfer is going to be enhanced at turbulent in turbulent flows, and because of that, because of this additional transfer, the skin friction and the heat transfer rate of heat transfer is going to be high. Skin friction is going to be high because the rate, the variation, the velocity gradient near the wall is going to be high because of the increased transport rate. Heat transfer is going to be high because the additional convective current, because of the turbulent eddies, is going to have to increase the rate of transfer of thermal energy. So both these are higher, significantly high in turbulent flows. Now, at the same time, the skin friction coefficient. This is plots based on calculations, actually, computations, actually, numerical modeling, and this shows it's just a variation, the predictions in turbulent flow. As I mentioned, we don't have any theoretical models, so the data are either based on experimental studies or numerical studies. This is based on various approaches to numerical model. And what it shows is the skin friction, the wall skin friction coefficient as a function of Mach number. So for different models, the values are shown. Different turbulence modeling approaches, the values are shown here. They are all comparable within the levels of accuracy that can be expected. And what we see is that with increase in Mach number, there is a drop in skin friction coefficient. But this is what drops is skin friction coefficient, not the skin friction as such. Please remember that it's TW divided by half rho v square. So with increase in Mach number, the velocity squared is increasing, and that's the reason why this whole thing tends to fall. It's not that wall shear stress decreases. Wall shear stress actually increases with increase in Mach number. So this is for turbulent flow, the variation of skin friction coefficient with Mach number. So that's what we have here. So again, please remember that it's not shear stress what is dropping. It is tau w divided by half rho v squared, which is dropping with Mach number, and that is because this half v squared term here in the numerator. Though TW is actually growing. Similarly, the heat transfer. What is shown here is Stanton number. We know the heat transfer, the rate of heat transfer divided by thermal capacity of the fluid, that is on the y-axis. So it basically represents the rate of the heat transfer rate, and on the y-axis you have x-axis you have Reynolds number. These are similar to, actually rather analogous to the frictional charts you probably would have seen in fluid mechanics. Again, here you can see that the plots are provided for laminar flow and turbulent flow. So you just note the change, laminar flow and turbulent flow. And turbulent flow parameters are significantly higher than laminar flow. Now, for within laminar flow, you can see for different Mach numbers 2, 4, 6, 7, 8, 10, etc. For turbulent flow, also you have values for different Mach numbers. Okay, 2, 4, 6, 8, 10, etc. For a given Mach number, so if you take 4, the rate or the Stanton number, heat transfer rate, is going to non-dimensionalized heat transfer rate is going to be higher than the corresponding value for laminar. That is going to be higher for a given same set of in the same range of Reynolds numbers is going to be higher for turbulent flow as compared to the laminar flow. And that is another observation. And we also see that there is a region which is sort of in between, where probably the laminar or the turbulent effects can dominate, and that depends on whether the transition has actually taken place or not. And how do we determine transition? That's what, as I mentioned earlier, there are several parameters which dictate or which control whether the transition takes place in that particular Reynolds number range, or at what Reynolds number the transition takes place. So these are some information which actually helps both qualitatively as quantitatively estimate the effect of turbulence on laminar flow. So, effect of turbulence in hypersonic flows. So the values, for example, say 6, 8, 10 are particularly hypersonic range, and this kind of charts or data can be made use of to calculate the values of heat transfer and eventually heat transfer coefficient for such configurations. Similar data. So this is again based on experimental data. What is done? This set of experiments are done for a conical body. So what you see as the plot again, CH root of REX. This we had seen previously when we worked out the laminar similarity, boundary layer similarity analysis. There are also CH root REX is the parameter that was used to present the heat transfer rate. So here also you have CH root REX on the y-axis and RE on the REX on the x-axis. Now let's see what is implied by this graph. As we see here, with an increase in Reynolds number, there is an increase in CH value, CH root of REX. Basically, there is an increase in heat transfer rate. A fairly steep rise actually. Now that there is a kind of a saturation that is coming up, but more importantly, we can see that in the lower range of Reynolds numbers, 2 into say or into 10 raised to 6, etc. 2, 3 into 10 raised to 6, etc. The laminar and what you see here as the horizontal line is based on laminar predictions, laminar theory predictions. So we can see that in the lower range, the experimental values practically compare well with the laminar theory predictions. So the boundary layer theory or the predictions based on the laminar approach are valid in the lower range of Reynolds numbers, and they are fairly close to experimental data. So these are actually a collection of data points. It's for as I mentioned, a conical body, and what you see as phi, etc. are these at different angles. Angles in the sense around the cone. So at different locations around the cone. Now the phi is not the included angle of the cone. Phi is the measurement locations around the cone. Okay, so these are some observations, some of the influences of turbulent flow, which are important in to be accounted in hypersonic flow. I stop here for now. We'll just discuss high temperature effects also. Probably we can finish that tomorrow as well. With that I stop. Any questions you can please ask. Okay, questions. So can I request the remaining teams to please give your assignment presentations? I guess group 3 also gave. Correct me. 4 and 5 are to be yet to be given, right? 1, 2, 1, 2, 4 has given. I'm sorry. Can you please remind me? I have noted it down. So who is
so group 3 has
due
still to present.
3. Can you present that now?
Yes, sir. Once again, I'll just share my screen.
Please do that.
Is it visible, sir?
1 second. Not yet. I think 1 second. No, I cannot see it yet. Others can see.
So now?
Yes, sir.
Is coming now. The presentation probably opening yet. Yeah.
Okay, sir.
Now it's visible. Yeah.
Okay. So these are my teammates. This assignment or task was to use the graph that was assigned to a group and try to digitize it and get the flight data. Here we used. I'll show you in the CP versus Excel X by L graph. We've taken the flight data from this particular graph that you can see that I've been zoomed into, and we've plotted it against the equivalence, the plot using the equivalence equation. So here, the flight data, the darker magenta color line that you can see is the flight data that we tried to get from the graph that was given to us. And the gray line that you can see, it's quite thin. That one was for the given alpha 39.8 degrees by using the equivalence equation. Now, the same thing was also done for half of the value of alpha. And you can see this is the graph that we got here. The magenta one is for the actual alpha 39.8 degrees, and the gray one is for 19.9 degrees, that is half of 39.8. Now in this one, you can see that because the image was quite pixelated at the starting right here, we weren't able to get a very clear flight data or say sharp or smooth flight data graph until 0.1. From there on, it is quite matching until we would say 0.5 to 0.6. It is almost matching. From there on, again there is a anomaly in the graph. So these were the observations, and we just inferred that the formula weakens or it does not hold at the trailing edge or where x by L reaches 1. That's all, sir.
This is good. The only thing that I want to remark on this is, so if you go to the first this one, go to the first slide where you showed the yeah. See the way the experimental data is shown. You have points, right?
Yes, sir.
See that? Right. So when you present, even for your comparison, when you present it, it's good to use. It's better to use such this one than having flat curves. I guess it applies to others also presented earlier. It's whenever you have experimental data, please use the dots also, because the dots will tell us where the measurements are available, at what points the measurements are available. Okay. For theory, you can use a continuous curve because it's available everywhere. Okay. This is a general suggestion when you present experimental data. Okay. Thank you. Carry on.
Okay, sir.
The
Thank you.
other team. Next team, please. 5. I guess.
Yes, sir. Sir, I think team 4 should present now.
Sorry, what did you say?
So no, sir, team 4 should present now. You said 5.
Okay, that's fine. Fine, carry
Is the screen visible, sir?
on. It's visible to me, yeah.
Okay, so good afternoon. We are group 4. So this was the plot that was given to us. We have an alpha of 40 and a Mach number of 21.6, and these two plots are for gamma 1.4 and gamma e equal to 1.18. So for the theoretical plots, we plotted using the hypersonic equivalency relation. We got this for Cp is equal to alpha and 40 and Cp alpha is equal to 20. So we go to the observations. The Cp decreases with the angle as there's a direct dependence on the angle. The other observations that we found were when it comes to the experimental plots, the dip in Cp when Z by L tends to 1 is absent in the theoretical plot, but when it comes to the experimental plots, we found a dip in Cp values. The Cp and the dip in the Cp values is more prominent in gamma E. So that's all we found.
What is that second point you said? So it depends. Can you go to the plot and explain what you mean by that?
Yes, the experimental setup we found we find that when Z by L tends to 1, there is a sudden dip in the.
That's okay. That every day is observed. Yeah, okay, that's fine. Yeah, I thought you were talking about the other end. Yeah, that's fine. Yeah.
Also, when gamma E is used, the dip is even more prominent. That's what we observed.
State that once again. Gamma. Sorry, what did you say?
So when gamma E is used, the dip is more prominent than when gamma is used.
I say, yeah, okay. It's a lot. Yeah, that's okay.
So that's also.
Okay. Thank you.
Thank you, sir.
So now, thanks. Which means I shall note it here. Yeah, Yuvraj Samivas and Sahana. Can you please give your presentation?
Sir, but we gave yesterday.
You gave, okay.
Yeah.
Yeah, great. Thank you. So are we done with all now? 1, 2, 3, 4. 4 is done. 3 is done. 2 is done. Okay. So I guess we are all groups are done. Okay. Thank you. Thanks to all of you. Bye. So we'll stop for the day. We'll meet tomorrow again. Thank you. Bye.
Thank you, sir.
Thank you. Thank you, sir.
Thank you.
Thank you. Thanks.
Thank you, sir.
Thank you.